presentation is a joint paper between the group of the Institute of Petroleum in Malmaison in France and also the group in the University of Strasbourg, and it's going to be presented by Dr. Chaumette. Higher alcohols and paraffin synthesis on cobalt-based catalysts, a comparison of the mechanistic aspects.
Can you move it a little bit, please? Center. Thank you. So as was just mentioned by Professor Ross, this work was performed in collaboration with the University of Strasbourg, Professor Kinman and Barbara Ernst, who is performing a PhD in Strasbourg at the moment, and of course by Dr. Kurti, who is at the head of the Kinetic and Catalysis department, and did a lot of job on alcohol synthesis catalyst and myself. We have been performing quite a lot of work studying the mechanism on copper cobalt-based catalysts with different French universities. And especially the University of Strasbourg, and looking at the trapping of intermediates on the surface of the catalyst. Also looking at coupling reactions. And what we found really is that the mechanism we can propose for Fischer-Tropsch synthesis towards hydrocarbons or alcohols really resembles the one that was just mentioned by Professor Sattler at the beginning of this afternoon session. In particular, we found that only C1 oxygenated species could be inserted into alkyl chains on the surface to form alcohols. We do not know which type of C1 oxygenated species it is, either for meal, formate, or CO. We could not separate the effects of these molecules, but indeed only C1 oxygenated species can be inserted, not C2 or T3, into alkyl chains containing a number of carbon atoms, which can be 1, 2, 3, 4, etc. Okay, so the proposed mechanism goes through CO and then for meal or formate, although there may be a route with previous CO dissociation into surface carbon, but all these two routes go to carbene species, which propagate on the catalyst to form higher hydrocarbons through hydrogenation and desorption. And you can insert a C1 oxygenated molecule into these carbene species and form acyl species which can be hydrogenated to higher alcohols. I did not realize coming here that it would be interesting to show you some Schulz-Flow reports. So many Schulz-Flow reports have been mentioned already in the literature and presented. But what I can do, please believe me, is tell you that we found really a Schulz-Flow distribution for the alcohols and also for the hydrocarbons. Of course, on copper cobalt-based catalysts, we found mainly linear alcohols. We found that the two Schulz-Flow plots were parallel for when you start from C1 up to, let's say, C10, C10 molecules, either hydrocarbons or alcohols. Afterwards, if you get too alpha distribution, the problem is that generally you get you favor the hydrocarbon formation rather than the alcohols. So the two Schulz-Flow plot cross themselves, okay, and are no more parallel. So this means that indeed there is a same primary mechanism for the formation of alcohol and hydrocarbon, at least on cobalt-based catalyst, and also I understand on rhodium-based catalyst, which comes from the fact that first you form primary intermediates which are carbene on the surface of your catalyst. What we did in this work I will present today is study alcohol synthesis catalysts, which are mentioned here, cobalt promoted by molybdenum and copper, with different formulations, and also some hydrocarbon synthesis catalysts, either cobalt on silica, those are on molybdenum, by the way, those are on alumina support, sorry. Those are on silica support, either unpromoted, promoted by ruthenium. You will see later on that also we made some experiments on lanthanum promoted, at least I will present one result on a lanthanum promoted catalyst. And also on another kind of promoter I will not mention since it's confidential, but at least you will see the results of the catalytic tests. Okay. Since the first step of the Fischer-Tropsch synthesis is CO dissociation leading to carbenes, we looked at the CO disproportionation experiment as a model experiment to try and classify the facility for different cobalt-based formulation, or the catalytic formulation I just presented, to favor the chain growth towards higher alcohols or higher hydrocarbons. So what we did is do 3 different CO disproportionation experiments, and in between looking at CO thermal desorption here, and here hydrogenation of the surface carbon which is formed since you disproportionate CO into CO2 and surface carbon. So this series of experiments allowed us to determine the activity of different cobalt-based catalysts in CO disproportionation to CO2, in surface carbon formation, and also the amount of CO that was chemisomed on the catalyst. So knowing all these data on different catalysts, we tried to correlate these data with the tendency of the catalyst to favor chain growth towards higher alcohols or higher hydrocarbons. You can see on this plot that indeed we got a good fit of the C2 plus hydrocarbon or C2 plus OH selectivity in carbon molar percent versus the CO disproportionation activity for all different catalysts, either alcohol synthesis catalysts, which are situated here, or hydrocarbon synthesis catalysts, which are here. Okay, only one point does not really fit on the curve. It's non-promoted cobalt silica catalyst with a very high cobalt content, up to 50% cobalt. In this region, you can have pretty high selectivity towards C2 plus hydrocarbon. These are catalysts which lead paraffins of heavy molecular weight, wax, indeed. And these catalysts are also very active, so they are indeed good catalysts for Fischer-Tropsch synthesis towards heavy paraffins. They are either cobalt-based catalysts, non-promoted but with a high cobalt content, not as this one, but rather high cobalt content, or promoted catalysts in which we had our promoter, our specific promoter, with a specific content, of course, an optimized content. Coming back to this general mechanism, as I mentioned already, the acyl species are the intermediates towards alcohol synthesis. But I mentioned that also hydrocarbons may be formed through formyl species which are absorbed, and then dissociation of the CO bound of the formyl moiety on the surface of the catalyst. So what we did is try to simulate these two ways, either CO bond rupture or simple hydrogenation to alcohols on cobalt-based catalyst with a model molecule, and of what we have already published in the past is that acetaldehyde, when it is absorbed on cobalt-based catalyst, really can mimic these two routes and can be either converted towards oxygenates or hydrocarbons. So let's look at what occurs when you absorb acetaldehyde and they then make it react by increasing the temperature of your catalyst bed. In these small experiments performed at lab scale on a few milligrams of catalyst, and thanks to online gas chromatography analysis, we were able to detect all these products. So here you have the cumulative response that we obtained on the catarometer versus the temperature. And here you have the detailed analysis we found through online gas chromatographic analysis. At low temperature, what you observe is ethanol and acetaldehyde desorption, so no reaction or simple hydrogenation of acetaldehyde. In the medium temperature range, you find some acetone, and in the high temperature range, hydrocarbons, methane, together with CO and CO2. This was obtained on the alcohol synthesis catalyst, copper, cobalt, molybdenum, or alumina. On hydrocarbon synthesis catalyst, you may find the same products, although here in this case you have a catalyst which is pretty selective towards hydrocarbons. So what you find is only acetaldehyde, ethanol through hydrogenation, and only methane at high temperature, no formation of acetone. Of course, here we have also CO and CO2 formation, which was not mentioned on this plot. Okay, so let me summarize and classify the products we find during the temperature program desorption of acetaldehyde on various cobalt-based catalysts. Pathway 1, adsorption of acetaldehyde, simple desorption, and hydrogenation. Pathway 2, which goes either through surface carbon or through hydrogenolysis of the CC bond or oxidation to acetate species. These are then decomposed or hydrogenated to methane and CO2. And pathway 3, you form acyl species, which may be trapped by methyl species present on the catalyst, and then form acetone. So you can form either oxygenated species or methane and higher hydrocarbons on the surface of your catalyst, starting with acetaldehyde. And what we try to do is take this second reaction as the one which would mimic the hydrocarbon synthesis, so the true Fischer-Tropsch synthesis on cobalt-based catalyst, and this one as the one which figures what we can obtain on alcohol synthesis catalyst, the alcohol synthesis routes. Let's have a look at what we obtained. We took as the criteria for hydrocarbon synthesis catalyst the ratio here, ratio R1, which gives the number of C1 molecules formed over the total number of C1 and C3 molecules, so here methane and here acetone in acetaldehyde experiments. So this was taken as the criteria to look at the orientation towards hydrocarbons formation on cobalt-based catalysts. You see in this table that for hydrocarbon synthesis catalyst H1 to H8, there is a good correlation between these criteria used in the temperature program desorption of acetaldehyde and the hydrocarbon selectivity which we found in Fischer-Tropsch experiments with the same catalyst performed in slurry bed reactor at a temperature comprised between 220 and 250 Celsius degrees, 30 bars, at a GHSV of around 1000 hours minus 1. Concerning the alcohol synthesis catalyst, we took as a criteria the ratio R3, which is the amount of C3 oxygenated species formed in the temperature programmed desorption of acetaldehyde over the total amount of methane and C3 oxygenated species. And again, there is a good fit with the C2 plus OH selectivity, the higher alcohol selectivity in carbon 1%, in alcohol synthesis experiment, which of course are not performed in the same conditions since we wanted to favor alcohol formation. So we perform these experiments at a higher pressure, 60 or 80 bars, and a higher GHSV also. The H2CO ratio, by the way, was pretty much the same, around 2. Okay. We can see on this plot, really, that we can put all the points I've just mentioned in the table on the same line, ratio R1, which figures the hydrocarbon selectivity on the catalyst. So there is a good fit between these criteria and the hydrocarbon selectivity of cobalt-based Fischer-Tropsch catalyst. And here a good fit between these R3 criteria, which give the C3 oxygenated species in the temperature programmed desorption of acetaldehyde, and the higher alcohol selectivity in the alcohol synthesis experiments. Let me come to a first conclusion. The temperature programmed desorption of acetaldehyde provides information on the tendency of cobalt-based catalysts to direct the changeovers either towards C2 plus alcohols or hydrocarbons. But they can also give you some insight into the effect of promoter contact. Here I have a plot of the percentage of methane which is formed during the temperature program of acetaldehyde on promoted cobalt-based catalyst versus the amount of lantana which we put on a cobalt silica catalyst. And you can see that depending on the amount of promoter you have, the percentage of methane you obtain is not the same. And also, for ethanol formation, you have a reverse tendency, decrease of ethanol, an optimum which is not situated at the same lanthanum contact. And you should look also at the other curve, which I have not taken here, but which is the amount of C3 oxygenated species, the amount of acetone which is formed during acetaldehyde thermodesorption, and have also another tendency. So really, acetaldehyde thermodesorption gives you an insight into the effect of promoters on cobalt-based catalysts and how they can orient the reaction towards alcohols or hydrocarbons. For those of you who are interested, we will present another lecture on this topic, more detailed presentation on this effect of promoters in the next Eurogas conference in Trondheim next week. Okay, what we performed also is hydrogen chemisorption and TPR experiment to predict the Fischer-Tropsch activity of promoted cobalt-based catalyst. I will not detail that. It is already well known from the work of Bartholomew, and also there have been some published work by Iglesias recently that you can use hydrogen chemisorption to look at the dispersion of cobalt on Fischer-Tropsch catalyst, and this gives, of course, an insight into the activity of your cobalt-based catalyst. I will not present these results. They will be presented in the next Eurogas conference also. I hope I have convinced you that the CO disproportionation into CO2 and surface carbon allows to evaluate the extent of change roles on cobalt-based catalysts, either towards C2 plus alcohol or C2 plus hydrocarbon. And using these simple tools, you avoid the long tests that you have to perform in a fixed bed or slurry bed unit under pressure to screen at lab scale your cobalt-based catalyst and know whether your promoters orient your reaction towards alcohols or hydrocarbons. Thank you for your attention.
Did I understand correctly, from acetaldehyde you find acetone only for those promoted catalysts which also have selectivity for oxygenates?
For oxygenates, yes.
That's very important. The mechanism you wrote, methyl group plus acyl group with acetone, suggests if both groups were on the metal, on the cobalt,
Yes.
you would always find it. But you find it only for the promoted catalyst. So it seems that one of these two reactants is not on the cobalt. Are you free to say what is your promoter?
I cannot say really what is the promoter.
An oxide?
In this, no, I cannot. Sorry.
Okay.
Silica has catalytic activity for converting acetaldehyde to acetone as well as to ethyl acetate. Did you verify that ethyl acetate wasn't formed and that the acetone didn't result from the secondary reaction on silica?
This you may see, but generally what occurs is that you see that acetone formation occurs at a much higher temperature. I did not mention here, but we also see in some case, especially on alcohol synthesis catalyst, some acetone formation at higher temperature than here, which follows another mechanism and which may be due to the reaction you mentioned.
What is the initial coverage of this TBD experiment? There are literature results which indicate like acetaldehyde can decomposition, selectivity of this acetaldehyde decomposition or reaction on the loading catalyst depend on the coverage of acetaldehyde. So my question is, what is the initial coverage of this, and do you find any dependence of selectivity on the coverage of the initial acetaldehyde?
I cannot really give you a figure of the surface coverage by acetaldehyde. Not in mind, but anyway, at the beginning, what we did is perform experiments with different concentration of acetaldehyde on the surface, and there is some dependence on of the selectivity with the coverage. Indeed, that's right. Something I did not mention is you may see here that we find that this ratio, we find this nearly exactly the same figures for ratio F3 and C2 plus alcohol selectivity. But really, if you change the surface coverage by acetaldehyde, this figure will change. So this is really a coincidence that we find the points on this curve. You know, the line can be this way, or can be here, or can be down, depending on the coverage, surface coverage by acetaldehyde. Any other question?
That being the case, then I take it off. Thank you very much. I think we should wait.